Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about prediction intervals for a particular response value y0. Okay? Okay. So, in another video, maybe you remember, we talked about confidence intervals for the expected value of our response variable at a particular combination of the predictor variables. Okay. Now we're going to talk about something related to that. But yeah, there are a few differences between a confidence interval and a prediction interval. Okay? Okay, so what we would like to do in this video is justify that this formula, this expression here, make sense. Okay? So as you can see, we have multiple regression model, right? It looks like this: y equals x beta plus epsilon. X is our design matrix. In this case, I'm using R for the number of regressors, right? In Walkerly's textbook, they use also K for the number of regressors. Okay, so now epsilon, this epsilon here is a vector, right? Epsilon 1, epsilon 2, up to epsilon k, right? Epsilon n, sorry. We're going to have as many errors as observations. And one way of rewriting our assumptions about the error, mean 0, right? Variance sigma square, and they are independent, so we could write this in terms of the epsilon vector, like normal, right, with a dimension n, a multivariate normal. We're going to have a vector of zeros with n zeros, and the covariance matrix is going to be sigma square times the identity, the dimension of that identity, n by n. Okay? Okay, so now I want you to see this, that this is very important, that we have a new observation, y0, okay? And that's the one that we're trying to predict that guy, okay? But again, this guy is a new observation and it's independent of our sample. We are going to make a note of that when we are doing our derivation. Okay. So since we're trying to predict that guy, we're going to pay attention to the forecast error, and which is going to be the difference between y0, right, and our prediction. Okay. Okay. Here we go. So first, as we said, our model looks something like this: y equals x beta plus epsilon. But we know that these guys have some dimensions. Y is n by 1, and let me write that down like this. I'm going to write this guy explicitly because it's important. Okay, y2 dot 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 yn. And let me write this guy like that. Okay, so it's I'm writing the transpose. Okay, so this is a column vector with n rows and one column. Okay, we said that x is going to have n rows, and it's going to have k plus 1 columns using you know, the notation from your one of your textbooks from Walkerly, k for the number of predictors, right? Okay. Epsilon n by 1 and well, we know that we're assuming that the elements that form that that vector, the epsilon i's, are normal with mean 0 and variance sigma square, right? Where epsilon I normal means 0, variance sigma squared. Okay. Remember that when we talked about the confidence interval for the expected value of y0, we proceeded in the following way. We made an analogy between what we had in the simple linear regression situation, and we said, well, basically, in general, confidence intervals are an estimate plus minus a margin of error. In this case, for the prediction interval, we're going to try and derive it in a different way. So you can see different approaches. Okay? Here we go. Just like before, remember that it would be a good idea to have very clear in our minds what's our target, what's our goal. So in this case, we would like to predict a particular observation. We could call it y0 or y star. Okay, so let's call it okay, y0. Okay. Now note that this guy looks like this, and remember that this guy y0, and that's why I'm doing it specifically, explicitly, is not one of these guys. Is not in your sample. It's a new guy, but it looks something like this. Beta 0 plus beta 1 beta 1 and x0 1, and then we're going to have beta 2 x0 2 dot dot dot, and then we have our k predictor. This is going to be yep, and this is going to be k. Okay, plus, right, a particular error term epsilon 0. So note that we are trying to predict this guy. Okay? That's our target. Now, what we're going to be using our estimator will be the expected value given this. And another thing that I want you to note is that we could write this down as x0 transpose times the vector beta plus that single error. Okay, note also that this is a 1 by 1 quantity. It's just a scalar, it's just a number. Okay, anyway, so if we compute the expected value of y0 given, and I'm going to be using the following notation, x0 represents a vector. Okay, I'm going to write it down just a sec. So I'm going to be using x0 transpose represents the following vector. Let me copy paste these guys so I can save some time here. So this row vector, this 1 by k plus 1 vector, is what I mean by x0 transpose as a vector. Okay, so this is what we're going to be using as our estimator, right? The expected value of y0 given x0 we're going to be using as the estimator for y0. Okay, and note that again, using matrix notation, this guy is that x0 transpose as a vector times the beta vector. Okay, and again, I'm thinking about the beta vector as a vector that contains as its elements beta 0, beta 1, beta 2, beta k. So this guy is a k by 1 vector, the beta. Well, k plus 1 by 1 vector. Okay. And now note that this guy, right, has dimension 1 by k plus 1. So it makes sense. When we do this multiplication, you end up with a 1 by 1 product. Okay? Make sense? Okay, so let me get rid of this, because the end result, this product x0 transpose beta, it's a 1 by 1. The only one that is k plus 1 by 1 is the beta vector. Okay, okay, just wanted you to see that. I want to make sure that we have our dimensions very clear here. Okay, so that's going to be our estimator, and let's say that we are going to be forecasting y0 this guy by x0 transpose beta which estimates this. Okay, make sense? This guy oh, sorry, this should be hat, right? Because the thing is, right, well, we found the expected value of this guy, which is given by this, and then we're going to show that if we take the expected value of this guy, you end up with this, which is not hard to do, right? Expected value of this quantity, right? Remember that in another video we talked about properties of expected values when we have this kind of situation, a matrix of constants and a vector of a random vector, right? So we can factor out that guy, and we know that the expected value of beta hat is going to be beta. Okay. So this guy here, right, what we're going to be using to estimate y0 happens to be an unbiased predictor. Okay? Okay. So now that's going to be our estimator, but let's talk about the covariance of this guy as well. The covariance of this guy, and again we also talked about something like this when we derived the formula for the confidence interval for the expected value. We know that if we want the covariance matrix of a matrix of constants times a random vector, what you end up with is, you can factor out this guy times, it would be the, in this case, the covariance of beta hat times this guy transpose. So it's just x0. Okay, there we are. Now we know that the covariance matrix of beta hat, and we show that also when we talked about that confidence interval for the expected value of y, is just sigma squared times x transpose x inverse. Remember? So x transpose x inverse we know that we can factor out this. That's it. Okay. So again, something that is going to be important is realizing, note that this guy here is 1 by 1, is a scalar. Okay? So that means that this covariance matrix, it's just a number. So what we have here is the variance of that guy. It's just a number. So it's just a variance. This is not a covariance matrix, really. It's just a number. It's a variance. Okay? Something else that is going to be important. Under the assumption that the errors, right, the epsilons, are normal with mean 0 and variance sigma squared, here let's see which quantity is going to be our estimator. x0 transpose beta hat, right? This guy is going to be our estimator of y0, right? Okay. Now, beta hat equals x transpose x inverse times x transpose y. So you can think about that as a matrix that pre-multiplies y, right? So it's beta hat is a linear combination of y's, and the y's are normal. Okay? So beta hat is a linear combination of normals, therefore will be normal. Now, take a look at this guy. X transpose beta hat. Beta hat is normal. So now x0 transpose beta hat is another linear combination of normals. So it's going to be normally distributed, right? And we know that a normal has two parameters that define the distribution. Its mean and its variance. What's the mean? The mean of this guy, of x transpose x0 transpose beta hat, is this guy, right? That's expected value, its mean. What's the variance of this guy? Sigma squared times x0 transpose times x transpose x inverse times x0, right? Note that this is a normal random variable, meaning it's a random variable. It is not a random vector. Okay, so it's one of those normals that we know and love from Statistics 256. Okay, okay, great. So now let's go back to our lecture notes. Since this guy is a random variable, we're trying to forecast that guy. Okay, we're going to try to predict it. So the quantity that we're going to pay special attention to is this, the forecast error. Okay, the difference between this guy, this random variable, and what we're going to be using to predict it. Okay, okay. So let's say something about y0. Let's study the distribution of y0. That's going to be important for us. So we can say something about the difference, the forecast error. Okay. So here we have the distribution of what we're going to be using to predict y0. So now let's say something about y0. Note that y0 what's going to be the distribution of y0? y0 looks like this, right? These are constants, the betas. The x's are also constants. So this guy here, epsilon 0, has a normal distribution. So that means that we have a constant plus a normal that's going to have a normal distribution, right? So the expected value of y0 is going to be this, beta 0 plus beta 1, x0, 1, and so on, right? And the expected value of this guy is 0, so normal with that mean and variance, hey, this is a bunch of constants, the only one that matters is this guy. So y0 has a normal distribution, this is the mean, variance sigma squared. Okay, so let me copy paste this. Normal, that's a mean, variance sigma squared. Let's rewrite that. This is just x0 transpose times beta, right? Or okay, now let's talk about the forecast error. Oh, come on. Forecast error. So it's the difference between what we observe and what we predict. Okay? So y0 minus x0 transpose beta hat. So difference between this guy and this guy. First, we have, and this is really, really important, y0 is independent, okay, of the others. We have, this is our y, this is our sample, right? And from this guy we get beta hat, right? This guy y0 is independent of these, right? So that means that x0 transpose beta hat is independent of this guy. Okay, so we have a sum of two independent normal random variables. So distribution of that guy is going to be normal, and it's going to be the mean of this guy minus the mean of this guy. But this is this x0 transpose beta minus this, right? So the mean will be 0. You guys agree? So let me write that down. It's going to be 0. Now the variance is going to be, it's the variance of a sum of independent random variables. So it's just the sum of variances. So it's going to be the variance of y0, which is this, sigma squared, plus variance of this guy. Because I know we have a -1, but remember that when we take the variance of a constant times a random variable, then you square the constant when you factor it out. So we end up with a +1. Okay, so another way of saying what we just another way of writing what we had there is, let's factor out that sigma squared, and we have that as the expression for the variance of the forecast error. Make sense? Okay. Now, so we know that at some point we would like to justify that we have a t-distribution. Okay, and we're going to do it in a different way from what we did for the expected value. Okay, because there we just said, okay, this is going to be similar to what we did in simple linear regression. Okay, so in this case I want you to see that it makes sense to use a t-distribution using distributional argument. So we know that t-distributions are by definition a ratio between a normal 0, 1 and a chi-square with n degrees of freedom. Okay? Well, the square root of a chi-square divided by its own degrees of freedom. That would be the definition of a t-distribution, right? Normal 0, 1 divided by the square root of a chi-square divided by its degrees of freedom. Okay? Okay, well, so let's try and make that normal 0, 1 appear. Okay, so what we have to do here is just standardize this quantity. Okay, so let me just say this. T-distribution. Trying to justify that we have a t-distribution there, we're going to be using that pivotal quantity, we call them, to construct that prediction interval. Okay, so let's use this. So what we're going to be doing is standardizing that guy. So what we're going to be doing here next is just dividing by the square root, okay, of that variance. And then we have a normal 0, 1, right? Okay. Now, I want you to remember something that we also know, right? We also know that if you have n minus k plus 1 times s squared divided by sigma squared, we have a chi-square with n minus k plus 1 degrees of freedom, right? So that's a result that we had from before, right? So n minus k plus 1 times s squared. I'm going to remind you in a sec what we mean by s squared. We know that that quantity has, given our conditions, right, has a chi-square. Where's that chi there? Chi-square with this n minus k plus 1 degrees of freedom. Okay. So when we had the simple linear regression model, k was 1. We only had one predictor. So what we had is n minus 2 times s squared divided by sigma squared is a chi-square with n minus 2 degrees of freedom. Remember? Okay. So, and remember that s square just represents an estimator of the variance sigma squared. So s squared just represents, and we know that an unbiased estimator of the variance is SSE divided by the appropriate number, right? So in the case of simple linear regression, it was n minus 2. In this case, it's going to be n minus k plus 1, k again being the number of predictors in your linear regression model. And we have another name for this guy. Remember, this is the mean square error. Okay? Okay. So, again, remember that by definition of a t-distribution is just a normal 0, 1 divided by the square root of a chi-square divided by its degrees of freedom. So this guy here, what we have here, would be our numerator. The one that we have here, it's a chi-square, so it's going to be our denominator. So now let's construct that t-distribution. So our t is going to be just, let's copy paste what we need here. This is our normal 0, 1. This guy here, we need the square root of that guy, and we also need to divide by the degrees of freedom, right? That's by the very definition of the t-distribution, okay? So what we have here then is just, let me rewrite what we have here. This would be the same as just, let me rewrite this like a product. So it would be the square root of sigma squared times the square root of 1 plus x 0 transpose x inverse x 0, right? So the square root of sigma squared would be just sigma, right? Let me do the same with this guy. We don't need this guy here. So what I want is a 1 over sigma here. That's what we're going to end up with if I do something similar, right? So now we would have this guy here, don't need this one. These are going to cancel out, right? So I'm going to have only, let me copy paste that, these cancel out, so I only have s squared. Agreed? Okay. Now note that these sigmas will cancel out, and then what I'm going to have, let me just copy paste the numerator here. I'm going to have a square root of s squared, right? Multiplying this. Another way of expressing that would be just, hey, let me place that s square inside the square root of that term, right? So let me place it inside here. And now this guy, that quantity, has a t distribution, right, with n minus k minus 1 degrees of freedom. So note that t, this guy here, our guy, has a t distribution with degrees of freedom n minus k minus 1. Just hit these guys here, right? This is the same as n minus k minus 1, right? And then we use this, as we would say in statistics 260, right, as a pivotal quantity. And when you solve for y0, right, you end up with this expression here. Your estimator plus minus your margin of error. Make sense? So can you see that that's what I meant at the end of the other video, where we discussed the confidence interval for the expected value of y0. Okay, that you know, that you could just based on what we know about the estimator and the distributional assumptions, just standardize it. You would have a normal, then you would divide by the right chi-square. In this case, the chi-square has to do with the estimator of the variance, right? And yeah, just you end up with t distribution. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.